Hello, everyone. I'm Tahmid, a fourth-year PhD student in the Social Sensing Lab, and today I'll be presenting my proposal, SophieSense, a novel integrated sensing paradigm built upon social and physical sensing for holistic situational awareness. So I'm going to start today's talk by giving you an outline of the talk. So I've divided my presentation into three segments. In the first part, I'm going to give you an overview of physical and social sensing, the motivation for SophieSense, and the key challenges in SophieSense. In the second portion of my talk, I'm going to cover the preliminary work that we have achieved so far that primarily covers social airborne sensing and social vehicular sensor network. In the third portion of our talk, I'm going to cover the proposed work that we intend to complete by the end of our thesis, which mainly comprises of SophieSense-driven urban anomaly investigation framework and a top-down, bottom-up social network for UAVs. I'm going to wrap up the talk by giving you a timeline for the remaining work to be done. So without further ado, let's move on to the introduction. So I will first give you an overview of traditional sensing paradigms. Afterward, I'm going to introduce you to the concept of SophieSense, the critical challenges involved in SophieSense, and provide an outline of our proposal. So let's look into physical sensing. Physical sensing is an avenue for reliable sensing that leverages hardware sensors for capturing information from the environment. So physical sensing in general has accurate information retrieval and has high availability. However, physical sensors have several limitations. Physical sensors are application specific and cannot be repurposed easily between different sensing applications. Physical sensors have limited autonomy and mobility. And lastly, physical sensors have high deployment and management costs. Let us now segue into social sensing. So social sensing is a rapidly evolving sensing paradigm that leverages human sensors to acquire knowledge from the environment. So social sensing has greater coverage, it's more economic, and enables multi-purpose sensing. And two examples of social sensing are crowd sensing and social media. Despite its numerous advantages, social sensing also has some limitations. First of all, social sensing has inconsistent reliability. So more often than not, sources on different online platforms tend to spread rumors, misinformation, and fake news, and that causes social sensing to be unreliable. Secondly, social sensing has limited sensing availability. So social sensing relies on the voluntary participation of users, and users can stop contributing sensing data to the system anytime they wish. As we have gone over the most two commonly used traditional sensing paradigm, let's look at the motivation for integrating social and physical sensing. So social sensing is versatile, is pervasive, has greater mobility, and is in general cheaper. By contrast, physical sensing has greater accuracy, it has faster sensing, and has high availability. Question is, can we obtain the human wisdom from social sensing and the hardware signals from physical sensing in order to get a more accurate and holistic representation of the environment? In other words, can we exploit the complementary nature of social and physical sensing? With that, I introduce you to SophieSense. So SophieSense is basically a portmanteau of the words social physical sensing. SophieSense is a novel integrated sensing paradigm that tends to unify the virtues of physical and social sensing. In other words, SophieSense intends to tell the story behind real-world occurrences that are happening constantly around us. So let us look into a few examples of SophieSense. The first example of SophieSense is an anomalistic crowd investigation framework where we can use social media and IoT data in order to understand the key reasons behind abnormal crowds. Second example of a SophieSense application is license plate recognition, where crowd sensing and vehicular sensor data can be integrated to identify the license plates of perpetrators or criminals on roads. The third application is damage detection using satellites and social media. And the last, most recent application of SophieSense is contact tracing, where social media and wearable sensor data is combined to contact communicable diseases such as COVID-19. As much as we want to combine social media with physical sensor, there are a few challenges involved. So the first important challenge in SophieSense is harvesting the reliable signals from the plethora of human and physical sensors spread throughout the world. The second challenge in SophieSense is handling the complex interactions within the human, cyber, and physical domains. The third challenge is adapting to the interrelated dynamics that arise from the social and physical realms. So with that, I introduce you to our proposal outline. So our proposal statement says, we want to construct social and physical active sensing frameworks, as well as system prototypes that holistically addresses these three key challenges that we have discussed so far. So as part of our proposal, in the preliminary work, we have developed two social physical sensing infrastructures, which are social airborne sensing, or SAS, and social vehicular sensor network. In the next part of our proposal, we intend to develop two further SophieSense infrastructures, which are Chirper, a top-down social network for UAVs, and SophieSense-driven urban anomaly investigation. And with that, I have presented you the proposal outline. I'm now going to move on to the next chapter of my talk, excuse me, where I introduce you to social airborne sensing. So let's look into post-disaster scenario. So during post-disaster scenarios, severe damages are constantly affected across different regions of an area. And such events require immediate attention from disaster response teams. So here's an example of a map where several disaster events are being reported constantly during a major disaster. So let's dive into more detail into a specific disaster situation that occurred during 2018 California campfire. We observed that in the span of just 4 days, more than 140,000 tweets have been posted. We also observed that many regions still had cellular access during that period. There is a map of an area that was affected by a California campfire. Here's a tweet of a person talking about the road closure during that campfire. Here's another tweet where a person posts about his dog, about his grandmother and her dog missing during the campfire. So the research question that we ask is, can we harness the social signals to drive UAVs for disaster response? So the question naturally comes to mind, why UAVs in particular? Why not other physical sensors? So UAVs have high speed, they have greater mobility, and also can enable wider sensing coverage. UAVs can fly to areas that are dangerous to response teams and can serve as actuators for delivering critical supplies during these emergency scenarios. With that, I introduce you to social airborne sensing. So social airborne sensing is a novel social UAV active sensing infrastructure that analyzes social signals on social media platforms such as Twitter and Facebook in order to identify disaster-related events. Afterward, the framework dispatches UAVs to event locations to verify the authenticity of the reports on social media using the hardware sensors on UAVs, such as cameras and infrared sensors. So here's an overview diagram of social airborne sensing, or SAS framework. So throughout the course of our preliminary work, we have developed 3 particular SAS frameworks, which are social drone, collab drone, and comm drone. So I'll dive into more details of each of those frameworks as I go along my talk. So let us look into some key challenges when we wish to integrate social sensing with UAV sensing. The first challenge is the noisy and unreliable social signals. So as we have already observed, social sensing is generally more unreliable due to the unvetted nature of the social media users. The second challenge is developing a closed loop system that tightly integrates the social sensing and the physical sensing components given their diverse characteristics. And the third challenge is the constraints that's introduced from the physical world and the social media. For example, the events can have revolving deadlines, and also the number of events that are reported on social media can widely vary over time. In order to address these challenges, we present the social drone framework, which is a closed-loop SaaS system for reliable event exploration. So social drone incorporates social signals to guide UAVs into those reported event locations, and afterward leverage the UAV observations as feedbacks for source pruning. So we consider a physical region of interest with a specific duration of sensing, as we can see in this figure. And to access the sensing process at reasonable granularity, we divide the sensing region into distinct boxes known as sensing cells. And we distribute the total duration of sensing into fixed intervals known as sensing cycles. So social media users report distinct events, and we assume that each of those events have a specified deadline associated with it. So given those parameters, the objective of social drone is to dispatch UAVs in order to identify the truthfulness of the events while respecting the deadline constraints. So mathematically, we formulate an optimization problem where the goal is to minimize the discrepancy between the predicted and the actual truth. Here's a solution overview of the social drone framework. So the social drone framework mainly consists of 3 key modules. The first module is the reliable source signal distillation module. The second module is a drone task allocation module. And the third module is known as the trustworthy source selection module. So I will not go into more details of the functionality of each of those modules. So let us look into the functionality of the first module. So the RSSD module's main functionality is to derive truthfulness score for each event using a technique known as truth discovery. So the concept of truth discovery is to analyze the relationship between the sources and their claims and estimate the veracity of the claims. In order to do this, we incorporate multiple truth discovery algorithms in our framework. In particular, we use the robust truth discovery algorithm, the expectation maximization algorithm, and the hubs and authorities algorithm. So let's take a closer look into how this truth discovery actually works. So here are a set of sensing cells, and we observe that 3 cells have reported events of fire. Here are 2 sources who are claiming that there is an actual fire. However, there's a third source who's mentioning that those claims are false. There is no fire in reality. So there is a level of conflict in these opinions. So what we do is we encode this information into a source claim matrix and feed this information to this ensemble truth discovery classifier, which gives us confidence scores for each of those events. We call this score the aggregate veracity. And mathematically, the aggregate veracity is a multiplication of expert weights and the expert veracity. So the expert weights are actually weights that are assigned to each of those ensemble algorithms. And this is determined using a technique known as proportional feedback control. So once we have this information from the reliable source signal module, the next task is to dispatch drones to the different location, which goes to this drone task allocation module. So let's suppose events A and B are actually true, but event C is false. And we have 2 drones, UAV1 and UAV2, which has to decide which location to fly first and then so on. So the DTA module uses a technique known as game theoretic task allocation in order to identify the optimal event locations for these UAVs to fly to. And in order to do that, we use a technique known as singleton weighted congestion game, which is a which is part of a bottom-up game theoretic approach. And in this function, we have three factors that govern the selection of the tasks. So the first factor is the uncertainty of the truth estimation. The second factor is the distance of that task from the location of the drone. And the third parameter is the remaining deadline of that particular event. The numerator of this function is cumulatively called the linear priority function. And the denominator is known as the congestion penalty. So what is the function of this congestion penalty? Let's take a closer look. So at every sensing cycle, multiple iterations are required for this function to converge and give conclusive values for the utilities. So let's say, for example, in iteration 1, we have 3 different utilities for each of those UAVs for these 3 different locations. And we observe that the utility for A is highest for both of the UAVs. So the question is, will both of the UAVs fly to location A? Well, to reduce this contention, what we do is we increase the value of the denominator by a factor of 1. And then we allow this game to run again in a second iteration. And we have now observed that the utility for location A is divided by 2, after which UAV1 has the highest utility of location B, and UAV2 has the highest utility for location A. So intuitively, the UAV1 will fly to location B, and UAV2 will fly to location A. Let's move on to the third module in our framework, the trustworthy source selection module. So the trustworthy source selection module's functionality is to discard unreliable sources from the system. And a key parameter in the trustworthy source selection module is the user reliability. So every time a user tells a lie, this user reliability score reduces for that user, and vice versa for telling the truth. So the module observes the dynamics of the events and the contribution of the sources and formulates a problem known as contextual multi-arm bandit, or CMAB. Our CMAB model comprises of 3 key parameters: the context, the action set, and the reward. So the context is further comprised of the number of sources at any given sensing cycle and the average contribution by the sources at that cycle. The action set is comprised of different thresholds of reliability scores to discard based on a selected action. And our reward function is basically the average accuracy at every sensing cycle. Mathematically, we formulate an optimization problem where the goal is to minimize the discrepancy between the expected reward and the actual reward. And we use the linear upper confidence bound to solve this problem. So in general, what we do is we use the UAV observations to discard unreliable sources from the system. So in order to evaluate the social drone framework, we selected a set of baselines that comprises of UAV only schemes, social sensing only schemes, and social and UAV combined schemes. For the data set, we selected the 2018 California campfire, where we obtained the tweets using a real-time Twitter data crawler. And we obtained the ground truth from different fact databases such as FEMA and USGS, as well as mainstream news media. For the event deadlines, we annotated them manually using historical event data and timelines derived from reliable sources, such as National Weather Service, CNN, NIST, and so on. Okay, so in order to evaluate the framework, we had to develop a simulation platform from scratch. So we acknowledge the fact that a real-world deployment of drones in a disaster response scenario is difficult because disaster situations are unpredictable and can hardly be replicated. So for that, we developed a trace-based simulation platform that consists of RDPilot drone simulator, Google Maps API, and Matlink protocol. Here's a screenshot of the simulation platform that's interfaced to the social drone platform. So let's look into the results for the event detection. So in terms of the accuracy, precision, recall, and F1 scores, we observed that social drone can more accurately identify the veracity of the events. And we attribute these performance gains compared to the baselines to the reliable source signal distillation module. Next, let's look at the deadline hit rate versus the total number of drones. So in this experiment, what we did was we varied the total number of drones from 10 to 20 based on the size of the map that we were experimenting on. And we observed that social drone achieves the highest deadline hit rate, which is approximately 10% better. And this performance gain is attributed to the bottom-up game theoretic task allocation in the drone task assignment module of the social drone. So what are the key takeaways from the development of social drone? We observed that the deadline hit rate could actually be improved. And certain events often exhibited some level of correlations in time and space. So the intuition is, if we can predict the event veracity based on these correlations, we do not need to actually send these UAVs to every single locations, because we can infer the veracity of certain locations, which will save us both the UAV resources and also allow us to achieve greater deadline hit rate. Which brings us to the next SAS framework called Collab Drone, a spatiotemporal aware SAS framework for selective event exploration in emergency scenarios. So the key task of Collab Drone is to identify repeated patterns of event veracity across different locations. Afterward, compute the correlations from those events and dispatch the UAVs to only the source events. However, there are few challenges in constructing such a spatiotemporal aware SAS. The first challenge is deducing the event confidence scores from the reported events and their associated deadlines. And the second challenge is the difficulty in identifying the correlation patterns among the different events. So in order to address these challenges, we present a modular solution for Collab Drone, which consists of 3 key modules again. The first module is known as the Social Sensing Information Distillation module, which has a similar principle as social drone. However, we have a new module now, which is the Composite Correlation Inference module, as well as the Drone Dispatch module. So let's look into the functionality of the Composite Correlation Inference module. So the CCI module predicts the event veracity using correlations. And in particular, this module observes the explored events for correlations and determines chains of correlations. So the intuition is we only dispatch the UAVs to the parent events or the events that has the highest root correlation indexes. Afterward, we can infer the veracity of the child events or all other events based on the veracity that we observe for the parent event. In particular, the CCI module identifies and computes 3 types of correlations. And I'm going to go into more details of these types of correlation in the next slide. So the first type of correlation is the temporal correlation. So the temporal correlation is associated with a repeated pattern of event attribute at a particular geolocation across subsequent sensing cycles. So for example, if event B follows event A across 2 different sensing cycles, then we can conclude that there is a temporal correlation between those 2 events. The next, the last 2 correlations are the lagged spatial correlation and the contemporaneous spatial correlation. So the lagged spatial correlation captures the propagation of event attributes across nearby geolocations. As an example, if event C follows event A and event E follows event B, we can say that event C and E has a lag spatial correlation. And the last type of correlation is a contemporaneous spatial correlation, where which captures the concurrency of event attributes across different nearby geolocations within a sensing cycle. So for example, if at one single sensing cycle, we observe that location D follows location E, we can conclude that there is a contemporaneous correlation between those two events. So the bottom line is A and B are parent events and the rest are child events. So for the drone dispatching module, we use a similar principle as the social drone framework, which is to compute a utility function. However, there is a fourth factor now, which is reliant on the correlation indices. So first, what we do is we derive a cumulative correlation score that quantifies the event location's usefulness in predicting other events, as well as prioritizing the exploration of events with high correlations. We also update our congestion rate, which is basically adjusted with the correlation of different sensing cells. And we plug in these values to compute the utility function. So looking into the evaluation results, we divided the dataset into 3 different regions. And we observed that in terms of the accuracy, precision, F1, and recall, Collab drone achieves better performance than its predecessor, as well as the other baselines. And that performance gain is mainly attributed to the composite correlation inference module. We also measured the average power consumption of each drone for each sensing cycle. And in order to obtain the power profiles, we benchmark a real UAV's power usage during takeoff, landing, and maneuvering. And afterward, we plugged in these values into the simulator to estimate the power consumption of each of the drone-based schemes. And we observed that Collab drone achieves better lower power consumption compared to the baselines. And this savings is mainly due to the inference of the different events where we do not actually have to send the drones to each and every single reported events. So let's look into the insights for Collab drone. As we have observed, if we can actually infer the propagation of events mathematically, we can actually save dispatching events to every single location. And a SAS framework can actually be tailored to be more application specific. For example, if we can only use a SAS for detecting a wildfire propagation, the performance can be further enhanced. The question that we ask is, can we expand the capabilities of SAS with a computational wildfire monitoring to detect the propagation of wildfire? And as a solution for that question, we developed ComDrone, which is a SAS framework for wildfire monitoring that integrates computational model into its solution approach. And we published this paper in 2016 DCOS. So that brings us to the close of the second chapter. I'm gonna now discuss about social vehicular sensor network. So the question that we ask is, should we use SAS for all different types of applications? As we have seen, SAS provides rapid disaster response, has reliable event veracity estimation. However, SAS requires dedicated pools of UAVs, which can be very expensive. And UAVs have limited flight times. Which brings us to vehicular sensor networks. So vehicular sensor networks are one type of physical sensing infrastructure that leverages existing vehicular infrastructure and employs voluntary participation of drivers. So compared to drones, vehicular sensor networks can provide even wider sensing scope. vehicular sensor networks have certain limitations. Car drivers are rational actors, and as we have already seen, human beings are unpredictable, and at any given time, car drivers can drop sensing tasks. Furthermore, VSNs have opportunistic event discovery, and only the regions that are traveled by the cars are discovered, as there is no incentive for this type of task completions. Let's look into critical resource discovery application. So during 2017 Hurricane Harvey, we observed that several people were tweeting about the availability of pharmacy, gas, and medicines in different regions of Texas. So the research question that we ask is, can we integrate social sensing with VSNs to expedite these post-disaster recoveries? Well, we can. There are again several challenges in melding social sensing and VSNs. The first challenge is the churn introduced by the car drivers. So car drivers, as we have already discussed, might randomly abort tasks due to personal reasons or whatever. And secondly, there are dynamics introduced by the physical world and social media, which again plagues social sensing and VSNs. For example, there could be far apart locations that are difficult for the car drivers to explore. There could be varying event deadlines, and these type of deadlines might drastically change over time. Lastly, there could be revolving social media reports, and the number of events that are being reported can sharply increase as time progresses. So in order to address those challenges, we introduce the social car framework and incentivize SVSN for critical resource discovery in emergency scenarios. The prime objective of social car is to exploit the collective powers of social sensing and VSNs. So here is the overview diagram of the social car framework. And the goal is to assign tasks to cars for exploring the reported locations. And after that, the car drivers identify the critical resources. So let us look into the underlying modules of the social car framework. So the social car framework consists of a social signal filtration module, which is similar to the functionality of social drone. Next, we have the vehicle task allocation module, and we have the dynamic incentive control module. Let's look into the functionality of the vehicle task allocation module. So the VTA module actually uses a very similar principle to social drone and collab drone. However, we now have a new parameter known as the reward for the tasks. We still have the distance to event location, the remaining deadline, and the event uncertainty. So how do we actually determine this new parameter known as the reward for the task? Well, that is actually done by the dynamic incentive control module. So the DIC module actually uses a top-down incentive allocation approach to assign reputation score to each car, which we term as PyTP. Afterward, we compute the aggregate reputation of all the cars in selecting a task. We base a reward for each of those tasks. And in order to adjust these rewards, we use a technique known as proportional integral derivative, or PID. And that is a well-known feedback control technique. So in order to evaluate the platform, we collected tweets during the 2017 Hurricane Harvey. And here are some statistics from the event. And in order to evaluate this new system, we could not actually use the drone-based simulation platform that we built for our earlier SAS frameworks. We had to actually resort to a new simulation platform that we developed by integrating Carla, which is an autonomous car simulator, with Google Maps API and an exposed Python API. So in terms of critical resource discovery performance, we observe that social car achieves greater accuracy in identifying the critical resources such as medicines and gas and food during post-disaster scenarios. So what are the insights from social car? Well, as much as we want to use social car during a post-disaster scenarios, there are a lot of cases where the roads can be untraversable. And that's due to the road damage caused by disasters such as hurricanes. And the dynamics of road damage actually makes it more difficult for the cars to explore. For example, new damages might appear over time, and damaged roads can get repaired. In order to address these concerns, we developed DASC, towards the road damage aware SVSN for scalable post-disaster recovery. And this paper was published in Pervasive and Mobile Computing Journal in 2020. With that, we finished the second portion of our talk and move towards the third portion, which is the proposed work. And the first of the proposed work is SOFI-sense-driven urban anomaly investigation. So urban anomaly investigation is a well-studied problem. And in present time, there are several methods for urban anomaly investigation, which includes surveillance cameras, cellular density tracking, and motion sensors. However, there are certain events that are unpredictable and highly transient, and it's very difficult to capture the dynamics of those events. For example, building collapses, sudden crowds, and traffic accidents. So let's focus more into one particular type of such transient occurrence, which is anomalistic crowd investigation. Let's look into a case study during 2020 Black Lives Matter campaign in the city of Portland, where a crowd is gathering for public demonstration. So here's a tweet where a person reports an anomalistic crowd instance in the city of Portland. And here's a snapshot of an UAV footage that was captured in the vicinity of that incident. The question that we ask is, can we develop an intelligent SAS framework to validate the existence of the crowds and infer their underlying attributes? However, before we answer that question, there are a few key research questions and challenges to be answered. The first question is how to handle the data sparsity in social signals and UAV footage. And the second key question is how to accurately infer the attributes of the crowd from the incoming data. So in order to address these challenges, we propose the Unravel framework, which is a SAS-empowered anomalistic crowd investigation framework that decisively identifies the anomalous crowds. And not only that, but also derive their underlying attributes in order to tell the exact reason behind the crowd gathering in the first place. So the next proposed work is a top-down, bottom-up social network for UAVs. So what is the motivation for a versatile UAV communication infrastructure? Or in other words, why is it important for UAVs to communicate effectively during a post-disaster scenario? Well, in a post-disaster environment, hundreds of UAVs operate simultaneously, and it is important for them to interchange important information, such as warnings, weather data, terrain information, and so on. We also have to note that these UAVs are most likely owned by different entities, such as firefighters, freelance search and rescue teams, as well as law enforcement officials. Due to all these reasons, there are often conflicting and redundant goals. So the key research question or challenges that we ask is, how can we foster trust and cooperation across these UAVs handled by diverse entities? And how can we handle the rational nature of the UAV operators? Or in other words, how do we address the churn issue that's introduced by these UAVs owned by different entities? The last research question that we ask is, how to enable a seamless interface for these heterogeneous UAVs to interact in a closed environment? Well, in order to address those research questions, we propose Chirper, a social network for UAVs owned by independent entities. So Chirper would basically enable vital information exchange during disaster recovery scenarios. And here is an overview figure of the Chirper platform, which has two main modules. So the first module is the bottom-up social structure, where the UAVs can establish friend-follower relationships among each other. And this basically mimics the functionality of a real human social media. For example, if different UAVs find complementary goals among each other, they can make friendship with each other. The next module of Chirper is a top-down reputation control module. So the function of this module is to periodically monitor the activity's performance and the telemetry data of each of those UAVs and assign a reputation score based on the historic behavior of the UAVs. So this principle is actually borrowed from the social car framework, where we use the reputation score to gauge the performance of the car drivers. Afterward, the top-down reputation control module rewards the good behavior of the cars and penalizes the bad behavior. And if you observe that the reputation score is below a certain threshold, the system is recommended to take some regulatory actions. For example, banning a certain UAV from obtaining information from the system or participation. And the goals of this proposal is to first develop a prototype of the Chirper platform, and afterward conduct hardware implementation and feasibility study using Chirper based on some real-world small-scale experiments. So lastly, I present you the tentative timeline for completing the proposed work. So currently, we're looking at the end of summer 2022 to complete the Unravel framework and conduct experiments across extensive data sets. And we intend to present the results of the research into IEEE Infocom. By fall 2022, we wish to complete the development of the Chirper framework, conduct hardware implementation and feasibility study, and we intend to publish the results into IEEE RTAS or some similar conferences or journals. And by the end of spring 2023, we intend to write the thesis defense paper and defend our thesis. And afterward, publish a paper into conferences such as IEEE DCAS, which aligns during that time. And here are the list of publications that I published during the course of my first few years of PhD. And thank you. I would like to take questions if you may ask.